A very good day to everyone. This is Komathi Murugan from Building Technology and Construction Management Division, Department of Civil Engineering, Indian Institute of Technology, Madras. I'm here to present my research on the effect of reinforcement overlap on the tensile behavior of textile reinforced concrete. Thanks to my team members, Mr. Sachin Paul, doctoral research scholar, and Professor Ravindra Gettu for the support and guidance through this research. With an immense pleasure to be a part of this 74th RILEM Week and 40th Cement and Concrete Science Conference 2020, let me go to the next slide. The contents of this presentation go this way. Starting with an introduction and a broad overview of this topic, I will explain the motivation behind this work. This is followed by an elaboration on the conducted experimental investigation with the discussion of the obtained results. Then I will conclude the presentation summarizing the work and highlighting the salient inferences. Textile reinforced concrete composite is used in this research. This composite is composed of fine-grained concrete or mortar as a matrix component with textile fabrics playing the role of reinforcement. It is one step ahead of the fiber reinforced concrete, where the tension properties of concrete are improved through random distribution of fibers, whereas here the engineered fabrics are oriented in the matrix to render improved performance in tension as well as in compression. In comparison to the conventional reinforced concrete, this TRC composite has a certain advantages. The first and the foremost being the non-corrosive reinforcement used in it, which revokes the necessity of thicker cover concrete and hence leading to the formation of thin and lightweight elements. With enhanced mechanical and durability properties, this material proves to be an economical and sustainable one. Such advantages make it suitable for numerous applications, both structural and non-structural, as well as its predominant role in retrofitting and rehabilitation of structures. Photos of it being used as a facade, a curtain wall, and as a jacket material in strengthening are shown here. As we all are aware, to use a reinforcement over longer spans, they need to be spliced due to their availability in restricted manufactured lengths. It means that there is a necessity of their connection which should be properly designed considering the stress developed at this joint and the required anchorage length. Textile reinforcement is no different in this aspect and it shall be spliced too. As we see here, there shall be two layers of textile reinforcement which are lapped. The mechanism at this region of overlap needs an examination. Scarce reports are available in literature examining the mechanical performance of textile reinforced concrete in the presence of overlaps. This research aims to probe this lacunae. Two objectives of this study will be presented now. First is to understand how the performance of textile reinforced concrete improves or deteriorates under tension in the presence of laps. This was probed by testing composites under tension over a range of laps. Second is to examine how a different textile with a different contact surface area over a particular length of lap behaves under tension. That is, for a single lap length, how the difference in the number of yarns or the mesh opening influences the behavior. Coming to the details on conducted experiments, to verify the first objective, 4 different lap conditions were considered, which were 50, 100, 150 and 200 mm laps for a particular textile. Specimens with no lap condition were also tested for comparison. The specimen dimensions conformed to the RILEM recommendations. To examine the second objective, 2 different types of textiles were selected. The first type is SBR coated e-glass textile with 15.7 mm by 10.1 mm of mesh opening, and the second type is an acrylic polymer coated AR glass textile with a bigger mesh size of 25 square millimeters. With 7 specimens for each combination, 70 specimens were tested under tension in total. The matrix used in this work comprised of cement, fly ash and silica fume as part of binder, quartz sand and quartz powder as part of aggregates, and super plasticizer all taken together at a water to binder ratio of 0.4. It resulted in a concrete with compressive strength around 40 megapascals. The prepared specimens were gripped as shown in the figure in an electromechanical testing machine and subjected to axial tension. Axial extensometers attached to the specimen and non-contact video extensometer were used to capture the test data. All the specimens were tested. Prominent failure patterns were revealed by the test. One was through rupture of textile at a crack, which showed the intact behavior of lap, and the other was through slip of textile layers at the spliced region. Now coming to the test results. The table shows the average values of stresses and strains considered for 4 specimens in each case at the salient points of first crack and peak for the considered range of laps for the first option of e-glass textile with a smaller mesh opening. The data corresponding to peak stress depicted in the bar chart shows that for 50 and 100 millimeters of lap lengths, the stresses were much lesser compared to the no lap condition, and it necessitates the provision of at least 150 millimeters of lap for this particular textile to depict a behavior similar to no lap condition. This is portrayed in the stress strain plot also, which shows the behavior of composite without lap. Now with 50 and 100 mm of laps, the behavior is still inferior to the no lap case. 150 lap is similar to no lap, and 200 lap case is much better, which almost shows a response similar to that of a double layer. The results for the second type of textile made of AR glass are here. The bar chart shows that there is not much improvement between the 50 and 100 millimeters of laps, and the performance is better with 150 and 200 millimeters of laps. This is portrayed in the stress strain behavior as well, where there is an improvement with an increased length of splicing. To summarize, this research aimed to probe the performance of textile reinforced concrete under tension with the condition of spliced reinforcement as to how the behavior will vary for different labs and for different textiles. Around 4 lab cases and 2 types of textiles were examined. The first set of results were presented here. It was observed that there is a certain drop in strength up to a particular lap length in comparison to a monolithic case without lap. For the chosen textiles, considerable performance was observed for a minimum lap length of 150 millimeters. However, it has to be noted that this was highly influenced not only by the size of mesh opening but also by the area of yarn available at each joint to transfer the stress. This work is under progress to understand much better the parameters influencing the stress transfer and to identify the variables necessary to normalize and model the behavior of textile reinforced concrete with overlaps. At this point, I would like to acknowledge the support from Indo-German Science and Technology Center, Science and Engineering Research Board, and the Fund for Improvement of Science and Technology Infrastructure in Universities and Higher Education Institutions by Department of Science and Technology, Government of India, to conduct this research. So, thank you very much, and any questions, please.